In this video, we're going to look at the organic halides and how they fit into the organic chemistry that we've learned so far. So remember we drew a chart that looked like this. We have the organic chemistry, and we broke that into the aromatics and the aliphatics. Well, you can also classify organic chemistry by looking at whether something are straight hydrocarbons or whether they are hydrocarbon derivatives. So you could do the same with the aromatics, but let's just do it over here with the aliphatics in this case. So if it's just a hydrocarbon, then it contains only C's and H's. So the alkanes, and the alkynes that we've done so far, we've only done branches of methyl, ethyl, propyl, etc. They were always carbon and hydrogen parent, carbon and hydrogen branches, and no other molecules. Those are hydrocarbons because that's all they contain, is hydrogen and carbon. The other group are what we call hydrocarbon derivatives. And most of the rest of the families that we're going to learn from here on out are hydrocarbon derivatives, which just means anything other than C's and H's getting attached to these molecules. So an oxygen or a halogen or different things like that all would fit into these hydrocarbon derivative type molecules. So the first hydrocarbon derivative we're going to learn about are the halogenated hydrocarbons. So remember, the halogens are right here. They're group 17. And specifically the ones you need to worry about are fluorine, chlorine, bromine, and iodine. Those are really the only four that you're going to see in Chem 30. And they are essentially just going to show up on our molecules as branches. So basically it's still an alkane, alkene, alkyne like it was before, but we're adding in a halogen branch somewhere in the molecule. Some things to know about them are that some organic halides are toxic and may be carcinogenic depending on the properties and how they're structured. So whenever we use these molecules in industry or in just general life, we always have to outweigh what's the benefit we get from using this chemical versus what is the risk. And that's true of all science. Does the benefit of using the technology or the science outweigh the risk that could come from it? So for example, I could maybe one day invent something that makes it easier to fold your clothes. Doesn't do it for you, it just makes your folds nicer. But the risk is there's a 95% chance your left arm will fall off. The benefit clearly doesn't outweigh the risk. But there are some things that we use every day that have some slight risks, but the benefit outweighs those risks, and then we try to find ways to mitigate the risks. Like, we're probably all burning natural gas in our homes to heat our water and to heat our homes and things like that. That has some risks of carbon monoxide poisoning if things aren't working properly, or even explosion if things are really going poorly. But we found ways to make them as safe as possible and ways to measure the risks and monitors to look out for carbon monoxide and things like that to balance the benefits with the risks. So the same with these chemicals. Some of them have some pretty substantial risks, but they may have benefits that make things worthwhile anyway. Another thing to keep in mind with these molecules is they are all synthetic. And I would write next to that in your notes, the word synthetic, write man-made. These don't occur in nature. All of these organic halides we have made in a lab somewhere. They're not something that you would find in nature. All right, now let's look at how we would jump into the naming. So in terms of the naming, finding the parent is going to be the same as it has been in the past. It's still our longest carbon chain. Although it has to be connected to the functional group, so in this case you have to have a carbon chain that's connected to the halogen. And we're just going to name these as branches. So it's a fluorine, for example, like this one is. It's a fluoro branch, sorry. If it's chlorine, it's chloro. bromine is bromo, and iodine is my favorite one, iodo. I don't know why I like that one. I feel like I should name a dog that one day. Come here, iodo. One day. All right, so if we look at this first example, let me switch screens. There we go. All right, so we've got our parent here, and we can count. It's a 1, 2, 3, 4, 5 carbon parent. So this is a pentane. In fact, we can write that out right now. Pentane. And the branch that I have, if I number this so that the branch gets the lowest number, or the functional group gets the lowest number in this case. Yeah, these are kind of weird. They're like the lowest importance functional group, but we'll count it. Would be this fluoro. So this is a 2-fluoropentane. Okay, really fairly straightforward. Just adding in a new branch. It's nothing crazy new to what we've already been doing. But let's do a couple of examples anyway. All right, our next one is this one. We have a 1 carbon parent, just the 1 carbon in the middle, so that's a methane. And I have 3 branches that are all chloro branches. So just like we did with our other branches, like a dimethyl or a trimethyl, the same thing here. So this is a trichloro. And since there's only 1 carbon for them to be attached to, I don't have to number it. So this is just a trichloromethane. I should have put those closer together. Remember that words just smash together. So trichloromethane is what's going to be on this one. Okay. Now we've got 2 different branches on this one. So my parent is the ethane in the center, but now I have a chloro branch and a bromo branch. And if I was numbering these branches, functional group doesn't help me, and branches doesn't help me here either because it's 1, 2 or it's 1, 2. So now I would use the alphabetical, that 3rd priority, because the first 2 didn't work. So I would put bromo as 1 and chloro as 2, just because of alphabetical. So this would be a 1, oh, don't need the dash at the beginning there, 1 dash bromo, 2 dash chloroethane. Right? Hopefully these are fairly straightforward for you. Okay, this one's a little bit more, well, a little bit larger. So now I have the longest carbon chain of all of this in the center. So I have 6. So I have a hexane. It's all single bond, so it's still a hexane parent. And I have 3 bromo branches, and I have 1 methyl branch. Now, for numbering, I'm going to get, if I number from the right side, I'm going to get 2, 2, 5, 5. If I number from the left side, I'm going to get 2, 2, 5, 5. So either way, lowest number for the branches or for the functional groups doesn't really help me in this case. But because of alphabetical rules, I would go with starting from the left so that the bromo has 2 and 2 and 5 instead of a 2 and 2 5s. So this is going to be a 2, 2, 5 tribromo and a 5 methyl, and then get me out of the way here, hexane. Okay, so hopefully that makes sense. If you're having any trouble at all with this, let me know, but it's fairly straightforward just with the branching and the stuff that we've already been doing. So hopefully it's not too crazy. Now in terms of the physical properties of these ones, the addition of the halide does tend to make these molecules more polar. And so when we remember back to our intermolecular bonding, if I have a fluorine on one side of the molecule, it will make that molecule more polar than if it was just a straight alkane. And being more polar is going to raise its boiling point and make it a more polar molecule when you start considering things like solubility. So just be aware of how these halogens are going to influence the molecules. Okay, some common organic halides to think about. Chloroform, if you watch any kind of old spy movies, I'm sure you've heard of chloroform before. It used to be used in actual like doctor's offices and things like that as an anesthetic to put people out for surgery or for dental work or something like that. I mean, now it's from spy movies where someone gets a rag thrown over their face so they get knocked out. That's chloroform. We don't really use it in legitimate purposes anymore because it has been known to have some carcinogenic properties. And the other one is chlorofluorocarbons. You may have seen labels like some of these on household products or aerosols or cleaning products. And the reason is because back in the day, we used chlorofluorocarbons for everything. They were fairly cheap to manufacture, they were very stable, and they worked great from everything from your refrigerator to your hairspray can or whatever. They were in a lot of different things. The problem was we discovered that the chemicals in the chlorofluorocarbons were destroying the ozone layer. So if you've ever learned about the ozone layer being destroyed, it was these chemicals that were doing it. In fact, one chlorofluorocarbon, if it reaches the ozone layer, can destroy up to 1,000 molecules of ozone. And it's really only been in the last 5 years or so that the ozone layer has kind of become more stable and is actually starting to regrow, and we're starting to reverse the damage that we did in the the 70s and the 80s, putting out all these chlorofluorocarbons and the damage that it did to the ozone layer. That's starting to reverse now that have got stricter controls and we don't use these nearly as much as we used to. So that's the organic halides. If you have any questions or concerns with any of this stuff, make sure you get in touch with me. Otherwise, see you on the next one.